Friends, when the new fundamental physical quantity amount of substance was added, a lot of new vocabulary was created. In this video, I will try to informally explain a few terms from the new vocabulary and their relation to the old vocabulary that we discussed in the previous video. Now let us say we have m grams of some element and say its atomic weight or relative atomic mass is AR. Then what is a gram atom of this element? You know, gram atom or gram atomic weight of any element is its atomic weight in grams. So 1 gram atom of this element is AR grams because AR is its atomic weight or relative atomic mass. Now my question is, how many gram atoms are there in this m grams of this element? That is easy to find out, right? Because if you have AR grams of this element, that means you have 1 gram atom of the element. But if you have m grams of that element, how many gram atoms are there? Let us call this small n. How do you get the value of small n? You know, you have to multiply these two terms and divide it with this term. So it will be m grams multiplied with 1 over AR grams, or simply m grams over AR grams, and that's what I have written here. So to get the number of gram atoms given the mass of an element, you have to divide the given mass with gram atom. Now if you move gram atom to the left hand side and the number of gram atoms to the right hand side, then gram atom will be equal to mass of the element over number of gram atoms. So gram atom is the ratio between these two terms. Similarly, if you have m grams of a molecular substance whose molecular weight or relative molecular mass is mr, then to get the number of moles, you have to divide the given mass of the substance with mole. And you know, the old definition of mole is its molecular weight in grams. So 1 mole of this substance would be mr grams because its molecular weight or relative molecular mass is mr. And if you move mole to the left hand side and number of moles to the right hand side, then this is the expression we get for mole. It is the ratio between these two terms. Similarly, the number of gram ions is equal to given mass of the ions over gram ion. And if IR is its ionic weight or relative ionic mass, then 1 gram ion is its ionic weight in grams. Similarly, the expression for gram ion would be mass of the ion or the given mass of the ions over number of gram ions. And for an ionic substance, number of gram formula weights would be mass of the substance given over gram formula weight. And again, if you move this to the left hand side and this to the right hand side, this would be the expression we get for the gram formula weight. See, all that we have done so far in this video is derive 4 expressions. 1 for the number of gram atoms, 1 for the number of moles, 1 for the number of gram ions, and 1 for the number of gram formula weights. And all the vocabulary that we have used so far is old vocabulary that existed even before 1971. Now in 1971, a new fundamental physical quantity called amount of substance was added to the SI system with the unit mole. And the symbol for this physical quantity is small n, and the symbol for its unit is MOL without the E at the end. Now my goal in this video is to introduce you to some of the new vocabulary without going into their formal definitions. Now, how do we understand this new fundamental physical quantity? Simple. This new fundamental physical quantity simply replaced all this old vocabulary. So, wherever you find these terms, you can simply replace them with this physical quantity, amount of substance, without changing the meaning of the sentence. But remember, these numbers are dimensionless, whereas amount of substance is a physical quantity and it has the unit mole. So, when you replace these old terms with amount of substance, don't forget to add the unit. Say somewhere you have a line like this: number of moles of methane is equal to 2. You can simply replace this number of moles with amount of substance, or you can simply call it amount of methane. Now remember, number of moles is simply a number without any unit next to it. Numbers do not have units. But amount of substance is a physical quantity and its unit is mole. So when you do this replacement, don't forget to add the unit. So amount of methane is 2 mole, not 2. Now what is the meaning of this sentence, amount of methane is equal to 2 mole? Remember, this fundamental physical quantity represents the number of particles present in the substance. And you know its unit is mole, and by definition the size of 1 mole is equal to this number, that is Avogadro's number. So if the amount of substance you have is 1 mole, that means you have an Avogadro's number of entities or particles. Obviously the converse is also true. If you have an Avogadro's number of particles or entities, that means the amount of substance you have is 1 mole. Here we are saying the amount of methane is equal to 2 mole. That means we are saying we have 2 times an Avogadro's number of particles or entities with us. But what are those particles? Are they atoms, molecules, ions, or something else? This does not tell the nature of the particles. But in this case, we can figure it out without any confusion, because here we are talking about the substance methane, and we know methane is a molecular substance and it is composed of molecules. So here we are clearly talking about methane molecules. So when we say the amount of methane is equal to 2 mole, we are saying we have 2 times an Avogadro's number of methane molecules. Now let us say we have this sentence that says number of moles of oxygen is equal to 1.6. Again, it is a dimensionless number. Now we can replace number of moles with amount of substance. So it becomes amount of substance of oxygen, or you can simply say amount of oxygen. Both are good. So amount of oxygen is equal to 1.6 mole, right? Don't forget to add the unit mole. So by this sentence, amount of oxygen is equal to 1.6 mole, we are saying that we have 1.6 times an Avogadro's number of particles with us. And this does not tell the nature of the particle, whether we are talking about atoms, molecules, or ions. And in this case, we cannot figure it out, because oxygen sometimes exists in the form of atoms and sometimes in the form of molecules. So when you say amount of oxygen is equal to 1.6 mole, I don't know whether you are talking about oxygen atoms or oxygen molecules. So in those cases, you have to clearly or explicitly mention the nature of the particles, like amount of oxygen molecules or amount of oxygen atoms. Because original sentence has number of moles, that means we are talking about molecules. So we have to say amount of oxygen molecules is equal to 1.6 mole. Then it means you are saying you have 1.6 times an Avogadro's number of oxygen molecules. Now instead, if you have a sentence like number of gram atoms of oxygen is equal to 2.7, then how do you rewrite this sentence using this physical quantity? You must say amount of oxygen atoms, because in the original sentence we have gram atoms, so you are talking about atoms, right? That is why you have to clearly indicate that you are referring to atoms by saying amount of oxygen atoms is equal to 2.7 mole. That means you are saying you have 2.7 times an Avogadro's number of oxygen atoms. Now you may ask, don't we have that confusion in the old vocabulary? No. In the old vocabulary, we have different names for different types of particles. Number of moles, number of gram atoms, gram ions, formula weights, etc. Now we replaced all of them with a single physical quantity. Because of that, sometimes we run into this kind of confusion. So to avoid that, you have to clearly indicate the kind of particles that you are talking about. Now for a moment, let's go back to our gram atoms, gram moles, gram ions, etc. For an element, by definition, 1 gram atom is equal to its atomic weight in grams. So the unit of gram atom is gram. It represents certain mass of the element. And here is the expression for gram atom. Gram atom is the ratio between mass of the element and number of gram atoms. The unit for the quantity present in the numerator is gram, and the quantity present in the denominator does not have any units because it is a number. Number of gram atoms is dimensionless. So the unit of this ratio is grams as expected. Now I said we can replace number of gram atoms with amount of substance. And amount of substance is a physical quantity and its unit is mole. Now after substitution, this ratio has the unit gram over mole or gram per mole. So this ratio no longer represents mass. So we cannot call this ratio gram atom anymore, because gram atom represents certain mass of the element and its unit must be gram. But when we replace it number of gram atoms with amount of substance that has the unit mole, we changed its dimensions. So this ratio must be given a new name, and the new name given is molar mass. So molar mass of an element is the ratio between mass of the element and amount of substance, and its unit is gram per mole. Similarly, for a molecular substance, if you replace number of moles with amount of substance that has the unit mole, this ratio no longer represents mole, because mole by definition, I mean the old mole, is its molecular weight in grams. Now after this substitution, this ratio will have the unit gram per mole. So we cannot call it mole anymore. And again, the name we use here is molar mass. So in all these cases, these old terms are replaced by molar mass when these denominators or when these numbers are replaced by the physical quantity amount of substance with the unit mole. And all these ratios have the unit gram per mole. So what we have done here is when we replaced these terms like number of gram atoms, number of moles, etc. with the physical quantity amount of substance, we also replaced these old names like gram atom, gram mole, gram ion, gram formula weight, etc. with a single name called molar mass. So molar mass in general is the ratio between mass of the substance and amount of substance, and its unit is gram per mole, also written as gram mole to the power of -1. And that is what we have here. See, all these old names are replaced by one new name called molar mass. Again, when you use this term molar mass, you must explicitly tell whether you are talking about atoms, molecules, or ions, etc. Because earlier we had different names for different kinds of particles. So by looking at the name, we can figure out the kind of particle that we are talking about. But because all these different names are replaced by a single name, you must clearly indicate the kind of particle that you are talking about. And this is the definition of molar mass. It is the ratio between mass of the substance and amount of substance. And its unit is gram per mole, always. Now, have you ever wondered why we took this weird looking number for the size of 1 mole instead of some nice round figure like 6 into 10 to the power of 23 or 2 into 10 to the power of 23 or just 10 to the power of 23? That is because if you take these many entities of a particular kind, then the total mass of those entities will be equal to its relative mass in grams. You will understand this with a couple of examples. Say you took 1 mole or an Avogadro's number of sodium atoms. Then the total mass of an Avogadro's number of sodium atoms or 1 mole of sodium atoms will be equal to its atomic weight or relative atomic mass, that is 23 in grams. Similarly, if you take 1 mole or an Avogadro's number of methane molecules, then the total mass of these many methane molecules would be equal to its molecular weight or relative molecular mass in grams. So mass of 1 mole of methane molecules will be 16 grams. Similarly, mass of 1 mole of or an Avogadro's number of nitrite ions will be equal to its ionic weight or relative ionic mass in grams. What is that? 14 plus 32, right? That is 46. So it will be 46 grams. So the mass of 1 mole or an Avogadro's number of nitrite ions is 46 grams. And such a relationship is very convenient. And it is for this reason we took this weird looking number for the size of 1 mole. So if you followed this, what I am saying is, if you took 1 mole of sodium, then its mass is equal to 23 grams. So now look at this ratio. If the amount of substance is 1 mole, then the mass of the substance is equal to 23 grams for sodium. So molar mass of sodium is equal to 23 gram per mole. And in general, for any element, molar mass is equal to its relative atomic mass or atomic weight in grams per mole. And using a similar argument, you can prove that molar mass of any molecular substance is equal to its molecular weight or relative molecular mass in gram per mole, and so on. So that is what I have depicted here. For an element or for atoms, molar mass is equal to its relative atomic mass in gram per mole. For molecules, molar mass is equal to its molecular weight or relative molecular mass in gram per mole. For an ionic substance, molar mass is equal to its formula weight or relative formula mass in gram per mole. And for an ion, molar mass is equal to its ionic weight or relative ionic mass in gram per mole, and so on. Therefore, molar mass can be defined as mass per 1 mole of substance, that is an Avogadro's number of particles. Remember, I am saying it is mass per mole of substance, not mass of 1 mole of substance. There is a subtle difference between the two. Now let us consolidate our understanding of molar mass with some examples. Now what is the molar mass of sodium? Sodium is always composed of sodium atoms, so we are asking for the molar mass of sodium atoms, that is mass per 1 mole of sodium atoms or an Avogadro's number of sodium atoms. And for any atom, molar mass is equal to its atomic weight or relative atomic mass in gram per mole. So molar mass of sodium atoms is equal to 23 gram per mole. Now what is the molar mass of oxygen? Here I have some confusion because oxygen can sometimes exist in the form of atoms, though it exists in the form of molecules most of the times. So you have to clearly tell me whether you are talking about oxygen atoms or oxygen molecules, otherwise I would not know. So if you are talking about the molar mass of oxygen atoms, that means you are looking for mass per 1 mole of oxygen atoms or an Avogadro's number of oxygen atoms. Again, for any atom, molar mass is equal to its atomic weight or relative atomic mass in gram per mole. So molar mass of oxygen atoms is equal to 16 gram per mole. And if you are talking about oxygen molecules, that is molar mass of oxygen molecules, it is equal to its molecular weight or relative molecular mass in gram per mole. So that means molar mass of oxygen molecules is equal to 32 gram per mole. And the molar mass of carbon dioxide similarly is equal to its molecular weight in gram per mole. And molar mass of sulfate ions is equal to its ionic weight or relative ionic mass in gram per mole. And the molar mass of sodium chloride, an ionic compound, is equal to its formula weight or relative formula mass in gram per mole. And the molar mass of electrons, that is mass per 1 mole of electrons, that is an Avogadro's number of electrons, is equal to this, because this is the relative mass of an electron. Similarly, molar mass of protons and molar mass of neutrons are shown here. And I don't think you have to memorize any of these numbers. Now pay attention to this important point. That is, the unit of molar mass is always gram per mole. It is never gram. That is why I kept on saying that it is mass per 1 mole, not mass of 1 mole. For me, mass of 1 mole must be expressed in units of mass, that is in grams. But the unit of molar mass is gram per mole. I think of molar mass as density. Density is mass over volume, right? That is mass per unit volume, not mass of a unit volume. Similarly, molar mass is equal to mass of the substance over amount of substance or mass per 1 mole of substance or 1 unit of amount of substance. And here is one last thing I would like to explain before we end this video. Say we have X number of molecules of a substance and we wanted to know the number of moles present in it. Here I am using mole in the old sense, that is molecular weight in grams. By using some simple reasoning, we can understand that 1 mole of all molecular substances contain the same number of molecules. I will explain that in a separate video. And in honor of Amido Avogadro, that number is called Avogadro's number. So understand that if you have an Avogadro's number of molecules, then you have 1 mole of the substance. That is its molecular weight in grams. Here we have X number of molecules, so how many moles do we have? Let us call this small n, and you know small n is equal to product of these two terms divided by capital N. So that is capital X times 1 over capital N, or simply X over N. So to get the number of moles, you have to divide the number of molecules given with Avogadro's number. To get an expression for Avogadro's number, let us move capital N to the left hand side and number of moles to the right hand side. Then capital N will be equal to capital X over small n. So Avogadro's number is the ratio between number of molecules and number of moles. And that is what we have here. Number of moles is equal to number of molecules over Avogadro's number, or Avogadro's number is equal to number of molecules over number of moles. And understand that this ratio is dimensionless because both in the numerator and denominator we have numbers that are dimensionless. Therefore, Avogadro's number is just a number without any units. But if you replace number of moles with amount of substance that has the unit mole, then suddenly this ratio will have a unit. So it becomes X over N mole. And you know X over N is equal to Avogadro's number. So if you replace X over N with capital N, we have N times 1 over mole. Now you cannot call this term Avogadro's number because Avogadro's number is dimensionless. But look at this term. This has the unit 1 over mole, also written as mole to the power of -1, read as per mole. So to represent this quantity, we have to come up with a new name, and that new name is Avogadro's constant, and it is represented by N with the subscript capital A. So Avogadro's constant Na is equal to Avogadro's number with the unit per mole. So numerically, Avogadro's constant and Avogadro's number have the same value, but they are technically not the same. Avogadro's number is dimensionless number, and Avogadro's constant has the dimension of per mole. So kindly notice this difference between Avogadro's constant and Avogadro's number.